Now we will discuss what is the magnetic field due to the circular loop carrying current, and in that particular condition we will discuss at a point which is just lying on the axial line. First of all, we are just considering a particular loop which is 3D, it is just perpendicular to the plane of the board, and radius of the loop is given here r, and current is taken anti-clockwise direction. Current in that particular condition is chosen anti-clockwise direction, and axially at the point P we want to find the magnetic field which is just situated on the plane of the screen or board, and the loop is just perpendicular to the board. Here x is the distance of the point P from the center of the loop, as well as small r is the position of the point P from the loop at the point where we are just considering a small length element dl. It is a particular small element situated at the upper part of the loop x y, and you know very well, according to the Biot Savarts law, always current element must to be chosen at a particular angle theta, which is given here 90 degree. It is a 3D figure, you know very well. When current element at the point C is, at the point C, current element is outwards. It is outwards, just coming from the screen at the outside. It is a current element, and it is just going inside of the board at the this one part. Then magnetic field must to be circular at this one point, like this one particular circle will form around to it, and magnetic field at a point P situated perpendicular. It is a tangential along to direction of the dV. Okay. So, here it is given, magnetic field will make angle 90 degree with the, you know very well, position of the r. It must to be 90 degree here, you know very well, because it is a radial and it is a tangential direction. It is a tangential and it is a radial direction for a small current element IDL situated here. And please see that particular angle is considered as a phi. Now we will dissolve the magnetic field dB in two different components, vertical as well as the horizontal, that is dB cos theta and dB sin theta. And you know very well, another component which is chosen here, it is the IDL dash. It is given as the IDL dash at x dash y dash. It is another part where current must to be entered inside of the loop. Here current was coming outwards and here current is going inwards. Due to that particular condition, that particular distance will also be small r, it is a position, and you know very well, magnetic field at this one point be also known as the dB dash will make angle 90 degree with the radial direction. Now, you know very well, in that particular situation we will find the another component of the magnetic field along to the vertical as well as the horizontal direction along to the given figure. Here you know very well, dB sin theta. dB sin theta is the component of the magnetic field directed along to the x axis, and dB cos theta as well as the dB cos theta due to the element, current element IDL here downward condition as well as the IDL here upward condition. Here it was outwards, here it is inward. In that particular scenario, you know very well, dB cos theta as well as dB cos theta downward and upward, both must to be equal and cancelled by each other. Therefore, you can say what is the condition finally we will get? You know very well, here the plane of the coil is considered perpendicular to the plane of the diagram, such that the direction of the magnetic field can be visualized on the plane of the diagram. And next condition will arise here, you know very well, at point C and D. It is a point C here and it is a point D here. Elements x, y and x dash, y dash are considered such that current at point C emerges out and at D enters into the plane of the diagram. It is very important to understand that particular loop is perpendicular on the plane, it is 3D figure. So, you must to be place the current ideal element in that particular part, downward part must to be entered inside of the board, and at this one point it will be outwards, which is also known as the ideal current element. So, finally, we will get the net magnetic field dB net we will find with the help of all the components of the dB sin theta. You know, it will provide the dB net. You know very well, number of the dl elements will be situated at the surface of the loop. Therefore, we will obtain the net magnetic field B, which must to be the integration of the all the small magnetic field along to the x axis, which is known as the dB net. So, finally, you can say capital B becomes integration of the all the small dB sin theta, and integrating it from the lower limit to the higher limit of the given condition. Now, with the help of Biot Savarts law, you can say magnetic field dB is given as the mu naught upon 4 pi I dl sin theta upon r square. It is a formula for the Biot Savarts law. You know very well now. Okay. Finally, we want to write the things. You know very well here, sin theta. Theta is the angle which was made by the loop with the position r. You know very well. In the previous video, I was just discussed condition here, ideal element, and it was the point P. What was the position of it? It is the position r, and that particular angle was theta, and that particular angle is shown in previous figure. It was the loop, and we want to find the magnetic field at the point P. Now, at this one position, it is a ideal current element which direction was outward. According to that particular situation, this one distance is treating as a position r, and this one distance is treating as a radius of the loop, and it was the perpendicular distance of the point P from the center of the loop. So, therefore, what will be the final condition? You know, here small r is the capital R square plus x square and root of it. It is a condition given according to the figure, you know. But at the point P, to the point this one was treating as a AB, you know, at this one condition, this particular angle is 90 degree, because it is a 3D figure. If ideal is just coming outward, then along to the z axis coming outward, it will make angle 90 degree with the position r. In that particular condition, you know very well, sin theta will be 90 degree. Therefore, you know sin 90 becomes theta becomes 90 degree. Therefore, sin 90 becomes 1. Clear? So, therefore, we will put the value in the Biot Savarts law. The dB becomes mu naught upon 4 pi I dl sin theta by r square is the formula, and when we will put the value of the sin theta, sin 90 as well as 1, so you know very well it becomes 1 here. It will provide the final formula dB equals to mu naught upon 4 pi I dl by r square is the formula. You know very well the angle theta between dl vector and the r vector is 90 degree, because the radius of the loop is very small, and since sin 90 is always 1. The semi vertical angle made by the position vector r to the loop is phi. It is the angle which r was just formed with the plane, you know very well, x axis, along to the x axis, and the angle between the position r and the dB is the 90 degree, you know, it is clear now. Therefore, the angle between the vertical axis and dB is also known as the phi, and dB is resolved into the two components. Now, you know very well, we was just revolving magnetic field in the two components, in which cos component was just cancelled out. So, due to diametrically opposite current element cos theta, components are always opposite to each other, and hence they cancel out each other. It was just discussed earlier, you know very well. And sin phi component, due to all current element dl vector get added up along to the same direction and in the direction away from the loop, mean to say along to the x axis, positive x axis, it will move away from the loop. It is very important to keep in your mind if you are just choosing a particular loop and just current element ideal is along to the outward direction at this one point. Again I am repeating here, and at this one point it is inwards. Suppose you know from the center of the loop at a particular point P where we want to find the magnetic field. In that particular condition, if current is treating as a anti-clockwise direction, then your net magnetic field at this one point must to be outward. Mean to say, total magnetic field will be outward from the center O along to the x axis along. Therefore, when we want to find the final value of the magnetic field, you know very well, net magnetic field is represented by the B here, and it must to be given like that. You know, finally we will get the result like B equals to integration of the all the components of the dB sin theta. And when we will integrate here, you know, it can be given as the mu naught upon 4 pi ideal sin phi. It is the angle, you know very well, which x axis will make with the position r divided by the r square. And do you know what is the r? Small r? Small r is given as the capital R plus x, capital R square plus x square and root of it. Is it clear now? According to the figure, previous figure, you know very well, it was the capital R, it was the x, and it was the small r in a right angle triangle. It was the center of the loop, and here it was the point P, and here current element ideal was situated. So, now you will get the result integrating. When we will integrate the dl with the proper limit, so you know very well integration of the dl is given as the 0 to 2 pi capital R for a given loop, because your loop was having the radius r. So, therefore, it will be 2 pi r minus 0 becomes 2 pi r, 2 pi r, and it is just given as here, you know very well, it is 2 pi r. And what is the value of sin phi? You know very well, sin phi is given as the, that particular angle was phi, therefore, sin phi is given as perpendicular capital R divided by the hypotenuse small r. Therefore, it becomes r divided by the capital R square plus x square to the power 1 by 2, half, you know. And it must to be given here like that. This one particular portion is given as value of the sin phi. Then finally, we will get the result. Please see here, you know, magnetic field, net magnetic field at the point P due to the loop is given mu naught upon 4 pi 2 pi I r square divided by r square plus x square to the power 3 by 2. Due to the multiplication of these two terms, it will becomes 3 by 2. And please do not cancel this one 2 pi with the 4 pi for maintaining the symmetry in the formula. So, therefore, you know very well, mu naught is the permeability of the free space, I is the current, r is the radius, and sin phi is the angle component of the magnetic field, are constants always. So, therefore, you will get the value of the small r, sin phi are replaced with the measurable and constant values, and finally, we will find the final formula as given in the board. It is the final formula of the magnetic field due to the loop at the point P, which must to be situated at the axis of it. Now, we will consider some special cases, and what are the cases here? First of all, we will discuss at a center O where x is 0. Suppose we are choosing a particular point, and if the observation point is far away from the coil, then you know very well, in that particular situation, radius of the loop is very less than the x. If point P, which was situated near to the x distance, is very far, then r square can be neglected. So, we are considering here two different special cases. First of all, you know very well, at the center as well as the very far distance from the loop, you know. And at that particular condition, please see on the board what should be the formula. I will explain and just graph for it. It is given in that particular situation. Please see on the board. Here it is given B equals to mu naught upon 4 pi 2 pi I over r. Why it is given here like that? You know, if x is 0, just putting the value of x equals to 0 in the previous formula and you will find the final formula for it. It is the magnetic field at the center. You know very well, it was the figure for the loop. Current is flowing anti-clockwise direction and this one point was the P. Now, this one point P is situated at the point O. Mean to say, we want to find the magnetic field at the center of it. So, what will the value? You know very well, its value becomes this one, mu naught 1 4 pi 2 pi I by r, by putting the value of x equals to 0 in the previous formula. And suppose if this one point P is very far, it is a point P which is very far from the loop. Mean to say, x is too much greater than the radius of the loop, then you will neglect the radius, r becomes 0. So, therefore, you will find the next formula with respect to that particular situation. You know very well, mu naught upon 4 pi 2 pi I r square divided by the x square. How it will get? You know, r equals to or r square equals to 0. Just putting the value of radius is 0 in the previous formula. And you know very well, in these two formulas, you know very well, magnetic field is inversely proportional to the distance and cube of it, its value will be square or cube of it. Mean to say, it will rapidly decreases. Therefore, it must be maximum at the center, you know, maximum at the center, but gradually when you will move away from the center, magnetic field will decrease, and you know very well, it will be a particular graph drawn for the forward direction along to the x axis, and for this one particular direction which is known as the minus x axis, that particular graph will be shown like that. Okay. Now, we will discuss different view of the direction of the current and magnetic field due to the circular loop of a coil. How? Please see on the board, that particular plane is given and suppose a particular current carrying loop is given which will produce the magnetic field. There are two different figures. With the help of these two figures, you can understand easily what is the direction of the magnetic field. If current loop is given in such a direction like a green part of given figure, you know very well, magnetic field with the help of right hand, Maxwell's right hand rule, you will apply the thumb at the point this one point is given where current is just releasing by plane cardboard, here it is given, it is incoming current, it is given here incoming, and it is entering current, outgoing current, you can say it is outwards and it is inwards here. You know, magnetic field will make such type of the loops here, okay, and here it will make, because you know very well, in that particular direction when you will put the thumb along to the direction of current in downward direction like that, therefore, magnetic field will make this type of the clockwise loops. Magnetic field will be also be circular here as well as here. Here it will form anti-clockwise and here it will form clockwise magnetic loops. Similarly, you know very well, it was also given your 10th standard, if a 3D loop is given here and current is flowing along to the direction of the anti-clockwise. Suppose it is just coming from this one point and entering at this one point. Therefore, magnetic loops must to be anti-clockwise at this one point and clockwise at this one point. How you will find the direction of it? With the help of Maxwell's right hand thumb rule. You know very well, with the help of that particular rule, you will find the direction of the magnetic field. So, now all these things are very easy and simpler for you.